Hello friends, welcome to another video in the playlist of digital electronics. We'll talk about variable entrant map today. It is a minimization technique and is a modification of K-map. I've written down few key points for VEM method. It increases the effective size of K-map and it can handle large number of variables, and we can write output in terms of inputs in VEM. I'll explain these key points as we do the example. Let's take up this example. A function that depends upon ABC has minterms 0, 1, 2 and 5. If we were to solve this function using a normal K-map technique, we would have drawn a K-map of 8 boxes and then would have minimized by pairing ones. But we can draw a 4-box K-map based off 2 variables, and we can express the third variable as the output. And how can we do that? Let's see. The first step is to draw the truth table. Of course, we see that the function is 1 at 0, 1, 2 and 5. But if we consider to express the output in terms of the variable c, what will happen then? Now, when we choose c, we can see that AB is changing 4 times. When AB is 0, 0, let's see what is the output, whether it depends upon C or not. We can clearly see when AB is 0, by keeping C as 0, the output is 1. By keeping C as 1, the output is 1. So the output is 1 nevertheless. So it does not depend upon C. So we can say for 0, 0 AB, the output is going to be 1 anyway. Let's look at the second case. When the input AB is 0, 1, 0, 1, we can have two cases. When C is 0, the output is 1. When C is 1, the output is 0. We can clearly see that the output is exactly complement of C. So I can express the output as C bar. In the third case, when the input AB is 1, 0, the output is exact replica of C. For C 0, the output is 0. For C 1, the output is 1. So I can say the output is C. And in the fourth case, when C is 0, the output is 0. When C is 1, the output is 0. So the output is not dependent upon C at all. It is keeping itself 0 in all the cases. So we'll say that the output is 0 for 1, 1 AB. It does not depend upon C at all. So now we can draw a K-map which is smaller than the actual K-map that we would have drawn. Normally, we would draw a K-map of A, B variables only. And for 0, 0 AB, the output is 1. For 0, 1 AB, the output is C bar. For 1, 0, the output is C, and for 1, 1, the output is 0. And how can we pair such variables is the next task. So let's look into that. Now here are the key points. A 3-variable function can be defined as a 2-variable function if output is written in terms of third variable. So we select the third variable and we'll work upon expressing the output as the third variable, and it is done with the process of converting the truth table into map entered variable. This C will be known as the map entered variable. So whatever mapping that we did for 0, 0, this is C bar, this is C, and this is 0. This is known as mapping of this map entered variable in the output block. Now there are some rules of mapping. A few rules have already been discussed here while I was trying to clarify this point as to how the output is dependent upon the map entered variable. So if we choose a variable, any variable, we need to see for both the values of the variable what is the output. So while changing the value of the variable from 0 to 1, if the output remains 0, we'll say that it is mapped to 0, and while it is changing, if it is keeping itself to 1, we'll say the output is mapped to 1. And for 0, if the output is 0, for 1, if the output is 1, we'll say it is equivalent to MEV, which was here in this case, which was equivalent to C. And if it is exactly the opposite, the output is opposite to that of your mapped enter variable, we'll say it is MEV, just like we saw here. And if for the value of map entered variable 0, we get a do not care and a 0. For 0 we get a do not care, for 1 we get a 0. We'll consider this do not care as 0 and the output will be 0. And if we have a 0 for 0 and do not care for 1, we'll consider this as 0 and we'll anyway get a 0. For 0, 1, if we get a do not care 1 and 1 do not care, then we get a 1 anyway, because we'll consider these do not cares as 1s for our convenience. And if for both 0 and 1 we get do not care, the mapping will be done to do not care itself. Then we have the VEM, variable entrant map, for this function as this. Now what are the rules to solve this map to minimize? So how to reduce? Step number 1 is to handle ones. So we have just one here, so we need to pair this one. How can we do that? To pair one or to handle all the ones, will remove all the MEVs. In this case there are two MEVs, C and C bar, so we'll convert those MEVs to 0 and then we'll see if one is making any pair or not. And to handle MEVs, we'll convert all the ones to do not cares. Let's see how can we achieve that. Step number 1 is to make all the MEVs as 0. So we'll make these MEVs as 0s and we are left with only ones here. We did not have do not cares, otherwise do not cares could also feature here. So we are left with a 1 here. So when I pair that one, it becomes A bar, B bar. Now in the next step, when we handle MEVs, we'll convert ones to do not cares, and they can help us in the pairing of MEVs. So this 1 was converted to X. Similarly here, this 1 was converted to X. So in the first case we take C only, in the second case we take C bar, and we get a pairing of this C with this do not care, and we get a B bar and the map enter variable. So the reduction is the common term out of this pairing multiplied with the MEV. So this is B bar C. Similarly, we have the common term A bar, and then the map entered variable itself was C bar, so it is A bar and C bar. And finally we have the function as A bar B bar plus B bar C plus A bar C bar, and we could verify that with a 3 variable K map also with these 8 blocks. So we have these 3 pairings which give us the same result. Now let's look at one more question here. Let's say we get this question where we have a few min terms and a few do not care terms. First step is to make the truth table. So I make the truth table of 4 variables, which will be 16 different combinations, and we have min terms featuring at 2, 3, 4, 5, 13 and 15. Do not cares are featuring at 8, 9, 10 and 11. You can fill the rest of the map values using these rules table. For example, when D is kept as 0 and 1, here in this case the output is kept constant at do not care, so I put a do not care here. Please understand phi and x are the same thing, do not care. And when it is 0, it is 0 here. When it is 1, it is 1 here. So it is mapped to D itself, which is MEV. And by chance we do not have any term which is D bar as its mapped value. But anyhow, we can still handle this, and let's say to handle ones, we'll make these D's as zeros. We'll keep only ones and do not cares and pair ones. So let's see what we have. And in order to handle D's, we'll make ones as do not cares. So by making these as zeros, what we are left with is we can pair one with this do not care, and this one is left all alone, and we get these two terms, B bar C plus A bar B C bar. When we wish to handle the MEV, which is D in our case, we'll change ones to do not cares, and they're not helping us in any way, but we still can get this pairing of 4 values, and which is equivalent to AD. So because the common term is A multiplied with the MEV, so we get the total output as B bar C plus A bar B C bar plus AD. Let's look at one more example. Before we take up any more example, I wish to show you that even if you would have solved this with a 16 box K-map, which is the 4 variable K-map, you would have gotten the same answer. You could pause the video and check it. Then let's get to this question. We can see this is a function of 4 variables, and the minterms are not given in the form of decimal numbers, so it becomes an additional task to find out minterms. And how do you find minterms? You multiply the missing variable D in whichever case to express all the SOP terms in A, B, C, D. And when I multiply these terms which do not have D with D plus D bar, I get these values, and from these values you can find out the minterms, again by converting them into decimals. Anything bar is 0, not a bar is 1. So this is 0 minterm, this is 1 minterm, this is 2 minterm, and so on and so forth. So this is an additional step that you might get in the questions where the minterms are not given directly. And the second step becomes drawing the truth table. Has minterms at 1, 2, 3, 4, 5, 6, 7, 8 and 13. Then it becomes easy to express. We select D as our MEV, so let's map it. For changing D, the output is 1, so I map it to 1. For changing D, the output is 1, so I map it to 1. Again 1, again 1, then the output is kept constant at 0, so 0, 0, and this is D, where the output is 0 for D is equal to 0, the output is 1 for D is equal to 1, so it is 0 D, and again a 0 here. A 3 variable K-map where this is D, and in order to handle ones we can make it as 0 and pair ones. These 4 ones will give me A bar, and in order to handle D I can make all these ones as do not cares and use them to our convenience in pairing of the MEVs. My MEV gets paired with this do not care, and it is B C bar D. So the total expression becomes A bar plus B C bar D. So this entire function could be reduced to this small value. This function was based on 4 variables, however it had a very small reduced form. So that's how variable entrant map is a very efficient technique of reduction as opposed to K-map, though it is clever and we need to follow some rules. But I hope this quick tutorial was of help, and if you liked the video, give it a thumbs up, consider subscribing. I'll see you in another video. Take care, bye bye.